Hello everybody, this is the notes for Calculus, section 6.4, Implicit Differentiation. So, what we're talking about here is finding the derivative of a different type of function. We've been dealing with just finding the regular derivative for a long time now, but those have all been things called explicit functions. Excuse me, we never really used that terminology, but it's just the idea of an explicit function is it is a function solved for y. So it says y equals something in terms of x. You know, y equals this one over here, x squared plus 5x minus natural log of x. It says y equals, and then everything else on the other side is just in terms of x. Okay, that's an explicit function. An implicit function is when the x's and y's are mixed together and you really can't solve for y. Or if you could solve for y, it just makes the function really ugly and nasty looking. So here is an example of an implicit function. You've got your x's and y's all mixed together. Lots of times what you'll see is some x's and y's together on the left side and on the right side of the equal sign. They're just all jumbled together. You can't just get y equals everything in terms of x. So that's an implicit function. So we're going to talk about how to find the derivative of that. Now, in order to do that, we got to talk about some notation. We have most of the time been dealing with something like finding f prime if you were given function f of x. If you were just given y equals, to find the derivative, the proper notation is that dy over dx. We're taking the derivative of function y with respect to x. Okay, we haven't used that notation very often lately. You know, when we first talked about derivatives, we used it, but it comes back into play a lot in the next several things that we're going to do. So, to solve for dy over dx, to find the derivative of y with respect to x. For an implicit function, what we're going to do is assume that y is a function of x. So when we see that variable y, it's something in terms of x. Now what it is, no idea. And it really doesn't matter. But that's what we're going to have to do. This idea of implicit differentiation. We're assuming that variable y is a function in terms of x. Okay? So, what we're going to do, these are your steps. Go ahead, hit pause, copy this stuff down. Step 1, differentiate on both sides of the equation with respect to x. Now, because y is assumed to be a function of x, this is the key thing right here. We got to do the chain rule on that variable y. And you'll see what I mean when we do an example or two. But that's the key thing. That's what makes implicit differentiation what it is. Anywhere where you see that variable y, you're assuming it's a function of x, which means you need to do the chain rule because there's a function inside there. So it's the derivative of the outside multiplied by the derivative of the inside. So, all terms with dy, in order to solve for dy over dx, any term that has that in it, we're going to move it to one side of the equal sign. And anything without that dy over dx, we're putting it on the other side of the equal sign. And then solving for that dy over dx. Now, it seems kind of weird just to write all this stuff down, so let's look at an example and it'll start to make more sense. So, we're going to find the derivative of this equation. 3x cubed minus 8y squared equals 10y. And before we find the derivative of this, I should probably just show you what an implicit function can look like. Here's an example of one. Okay, it's not a function. You know, it fails the vertical line test. It doesn't have an inverse that's a function. It fails the horizontal line test. But it's a nice looking graph. It kind of looks like the infinity symbol. The function, you really can't see it. Let's see if I can write it here. Of course, the board's not working properly. But it's 3 times x squared plus y squared, quantity squared equals 25 times the quantity of x squared minus y squared. Very complicated function, but it gives us this nice looking graph. So, that's an implicit function. We're dealing with one here. We want to find the derivative of this. So, basically, you're going to take the derivative of every single term. If it has just an x in it, you're just going to do everything like normal. So for this first term, 3x cubed, the derivative of that, 9x squared. just like normal. For the next term, let's change colors here. It's a variable y. So we're assuming y is a function in terms of x. We're going to do a chain rule. So that exponent of 2 gets multiplied out in front. So minus 16. We decrease that exponent of 1. The inside stuff, that y, stays the same. But then we multiply by the derivative of the inside function. I have no idea what that y is, what function y is. But that's what this represents. It's the derivative of that inside function with respect to x. So this is the idea of the chain rule. The derivative of the outside multiplied by the derivative of the inside equals, so now we just go to the next term on the other side of the equal sign, 10y. This is technically an exponent of 1, so when we're going to do a chain rule again because it's the variable y. So 10 times 1 is 10. Try to move this away here. The y goes to the 0 power, so it's not there anymore. But then we have to multiply by the derivative of the inside function, which is that dy dx. So anytime you have that variable y, this is what's going to happen. You're going to do a chain rule, but you always have to end up multiplying by that dy dx. That's the derivative of that inside function, that y. We're assuming y is a function of x. Okay, so the next thing, this is the differentiate part, this is find the derivative of each term. Now we're on to step 2. Isolate terms with dy dx on one side of the equal sign. So I'm going to keep this 9x squared here on the left side of the equal sign, which means I need to add this term to the other side. So I got 10 dy over dx. I'm adding 16y dy over dx. Okay, then what it says in step 3 is to factor out the dy over dx. So if you look at these two terms on the right side of the equal sign, they both have a factor of dy over dx. So I'm going to factor that out. What I'm left with is 10 from that first term plus 16y from the second term. And that equals 9x squared. Okay. It says next step is and solve for dy over dx. That's a multiplication here. We want dy over dx to be by itself on this side of the equal sign. So because it's a multiplication, I'm going to divide by that quantity. So I got 9x squared. That gets divided by 10 plus 16y. This is our derivative. This is dy over dx. That's the derivative of y with respect to x. It equals 9x squared divided by the quantity 10 plus 16y. So that's just one example. I'm going to do some other videos doing some more examples where they get a little bit more complicated. Just more things to think about, product rule, quotient rule, things like that. All right.